Good morning, everybody. Today we will continue with our series of internal seminars. And today we have Alan Rios, who is a student of Tomeu Fiorn, and he will tell us about Wilson loop operators, which, as we know, is they play a crucial role in theories of QCD and of course a crucial role in the universe, no? Since their properties indicate whether the QCD is a confining theory or not. So let's Alan to tell us about this, and so please, Alan, you can start.
Okay, so let me first thank Jorge for the kind introduction and the invitation to give a talk here at this new series of seminars that we are holding at the Institute. So, as Jorge was pointing out, the idea of this talk is going to be to introduce the Wilson loop operator in gauge theories and to try to tell you how, by studying this Wilson loop operator, we can find and probe new structures within gauge theories and what kind of things we can learn by studying this operator. Okay, since we are going to be mostly discussing gauge theories or quantum field theories, let me first start by making a really brief history of the field and of what do we understand now by particle physics, so we can summarize our understanding by many iterations of this process in which we try to ask the question of what thing is most fundamental, and by answering this question we start to build models that gives us certain rules in order to understand nature. Okay, so after many iterations we have reached to this point in which we have a more fancy way of doing this experiment at the LHC, in which we are probing our current understanding of particle physics, and in particular we are probing what we call the standard model of particle physics. Okay, so the standard model is our current understanding that gives us a set of rules for which the different particles can interact, and by probing this set of rules we try to find new physics and try to discover new things within the framework that we work. Okay, so up to good accuracy, quantum field theory seems to describe our universe, or at least a part of our universe, because of course I'm not going to be talking about a quantum description of gravity, because we still lack that description, despite the fact that we have a candidate for a quantum theory of gravity, that's quantum string theory. But during this talk, I'm going to be mostly discussing quantum field theory without talking about gravity. Okay, so by studying this standard model and doing the experiments, we've been able to find the Higgs boson, and with this we have completed our current understanding of the standard model of particle physics, in which we have different generations of particles. We have the gauge bosons and we have the Higgs bosons, and all of this content is understood in terms of quantum fields. Okay, but using quantum field is not only suitable for particle physics, but we can also study problems in many different areas of modern physics. For example, we can try to solve problems in condensed matter by using quantum fields. So for example, we can try to use quantum field theory in order to try to understand the fractional quantum Hall effect. We can try to understand quantum phase transitions or phase transitions and many other phenomena in nature. Okay, so what we see is that quantum field theory plays a fundamental role and is a fundamental tool that allows us to study different phenomena in different areas of physics. Okay, so thus, by understanding quantum field theory, we can understand better nature. Okay, and within quantum field theory, we can study many different things, but let me introduce the operator that's going to be relevant for us in this talk, and that's the Wilson loop. Okay, so the Wilson loop is an operator that we can define in any gauge theory, and they are essentially phase factors associated to charged particles under the gauge field. Okay, we can think of them as comparators or as the parallel transport for the gauge field. Okay, so if here you can see the pointer, in order to define the Wilson loop, we need the gauge field that here is a mu. We need a path that the charged particle is going to be following in space-time. And we couple this gauge field to the trajectory of the particle here with this differential that encodes the trajectory of the particle. And we also need the charge of the particle that in this case I'm setting to 1. Okay, and we are going to see that by studying this operator and how is its dependence with the choice of path and the choice of charge, what can we learn by studying it? Okay, and it's going to play a fundamental role in the formulation of lattice QCD, and as I am going to be showing you next, it has many different and interesting physics hidden in its expectation values. But in order to gain a little bit more of insight of what do we mean with the Wilson loop, what does it mean for it to be a parallel transport of a gauge field? Okay, so let us step back a bit and discuss the concept of parallel transport in geometry that we might be a bit more familiar with. And if we are not more familiar with it, it doesn't mind, because at least it has a really pictorial way in which we can understand it, okay? So we are going to grab our favorite manifold. In this case, it's a sphere, and we choose a path that here is going from A to the North Pole, then to B, and then we go back to A. Okay, and we grab a vector and we start moving it around this path. And once we go back to the starting point, we compare it with the vector that we started with. In this case, we see that the vector has a shift in an angle alpha, okay? And this is pointing us to the fact that this manifold has curvature, okay? But how can we interpret this with gauge fields when we have a different gauge field at each point in space-time? Okay, so what does it mean to compare the gauge field in space-time? So in order to do that, let me introduce an analogy in which, instead of discussing a space-time and gauge fields, I'm going to replace a space-time by these 3 blobs. Okay, so this serves as a role of discretization, if you want, or a kind of a lattice for a space-time. And instead of thinking of gauge fields, I'm going to be talking about money, okay? And we are going to be the ones that are going to be following a trajectory. Here is this green line that we are going to be following. And at each point, we are going to perform a comparison that's going to be analogous to the one that we will do with the gauge field, okay? So we are going to be starting here at this point that's represented by the United States. And we are going to be starting with money, with $1, okay? That will be our initial configuration of the gauge field. And then we go to Argentina, and we are right there, and we have our dollar, and we compare it to the currency in Argentina, okay? So we are comparing 2 different kinds of currency, and that's similar to comparing 2 different configurations of the gauge fields. And we see that we have $1 that equals 10 pesos, totally fine. And we grab these 10 pesos and we follow the line and we go to Europe and we perform the same thing, okay? So this is like going to another point in space-time. We compare it once again with the configuration in Europe, okay? So in Europe, the configuration is in terms of euros. So we have that 10 pesos, it's €1, totally fine again. And then we go back to the United States of America and we compare once again, and we see that now $1 is 1.5, sorry, €1 is $1.5, okay? So if we compare with the starting point that was $1, we ended up with an earning of 50%, okay? So this is a difference in the configuration of the gauge field, okay? It's similar to the angle that we were discussing before in the case of geometry. But the important thing here is that in the case of gauge fields, this phase is observable, okay? This is something that we can go and measure in the lab. So a famous example is the Von-Aronoff effect, in which we have a magnetic field here in the center, and depending on the path that we choose, we have a different phase, and this phase is observable. Okay, so we can measure this difference in the phase, and that's exactly the von-Aronoff effect. So what happens if we choose a different trajectory? Okay,
but Alan, let me ask, in the picture you had before, is this exactly equal? No, the one with the magnetic field.
Yeah.
So this gives, I mean, the integration along the closed path give me 2 pi the intensity of the current. So, I mean, is this the same that I do in electrodynamics when I have when I compute this circulation of the magnetic field?
Yes, the important thing here is that depending on the path that you choose, so you have 2 different paths, and there is a difference in the phase because of the particle, if its charge is coupling to the gauge field, and in particular to the magnetic field, and depending on which path you are taking, you end up with a measurable phase. And it's related, of course, with the flux, the magnetic thing.
But here, if I can deform a path into another without crossing this.
Yeah, but the thing is that this space is not simply connected. So in principle, you can't do that.
Yeah, I mean, but there are some paths which I can connect from one to the other.
Yes.
I guess that when I compute Wilson loops, there are paths that I can connect for which the Wilson loop is not the same. Am I right? Or?
So you are thinking about having a path and then deforming the path and thinking if it gives the same or not.
Yes.
Well, in principle, it depends. No, for me, it's not obvious that it's going to be the same. In principle, it should be different. That, despite the fact that I mean, if it's an infinitesimal deformation, it's going to be fine. But if you do something bigger, it's not going to be the same, I think.
Okay.
Okay. Okay. So we can also, if we choose a different trajectory, we can study the phases of the field theory. Okay. So in order to do that, we can consider a rectangular contour. Okay. And by studying this contour in particular, what we are doing is we are studying a pair of particles and antiparticles. Okay. And how's that? Remember that the Wilson loop couples to a charged particle. And here, when the charged particle is going back in time, we can think of it as an antiparticle. So effectively, we are studying a pair of particles and antiparticles. Okay, but the interesting point is that if we study the expectation value of the Wilson loop, this expectation value gives us the potential energy between this pair of particles. Okay, so depending which theory we are considering, we are going to be studying this potential energy. Okay, so this interaction between the pair and antiparticle pair. So for example, if we consider Maxwell theory or a U1 gauge theory, and we perform this computation, we see that the interaction between the particle and antiparticle is given by the Coulomb interaction. Okay, but if now we do the same computations for pure Young-Mills, we see that now the potential is given by a linear term in the separation between the particles, okay? And this is telling us that if we want to break apart a pair of particle and antiparticle, we need an infinite amount of energy. Okay, so we see that by studying the expectation value of this operator, we can extract sensible information about the gauge theory that we're studying. But we can also study another trajectory that's going to be relevant for us, and that's a cusp trajectory, in which we can think that we have a particle sitting, okay, so it's a particle that's not moving, and we are suddenly giving it a kick, okay, and we are starting to move the particle with a sudden kick, so we have a cusp in the trajectory, and we can think that this trajectory is not differentiable, okay? And since it's not differentiable, it's going to introduce some kind of divergency, and more physically, we can think of this divergency as characterizing the radiation that the particle is going to start emitting once we kick the particle. Okay? And effectively, if we compute the expectation value of the Wilson loop in this trajectory, we see that we have the divergency over here, but we also have this quantity that's called the cusp anomalous dimension that depends on the coupling of the theory and also on the angle that we are forcing the particle to move. And this cusp anomalous dimension characterizes many interesting physical phenomena. Okay, so what will be relevant for us is the small angle expansion of this quantity. And with this small angle expansion, we can characterize the energy radiated by a probe particle. Okay, so the energy loss or the radiation of the particle. And that's given by this formula over here. Okay, so we see that if we want to study the radiation emitted by a probe particle in an arbitrary gauge theory, it's enough for us to characterize the expectation value of the Wilson loop. Okay, and for those of you who know, this is an extension or a generalization of the famous Larmor formula in Maxwell theory. Okay. So far, what we have seen.
Sorry, what is that derivative respect to? So
okay, so I'm hiding a bit of information here, but this derivative is a derivative with respect of the coupling of the theory. Okay, but yes, essentially the important thing, the takeaway message from here is that if you compute the Wilson loop in a given configuration, you can characterize the radiation. Okay, but of course, what we have seen so far is that the Wilson loop has many different and interesting properties of the gauge theory that we are studying. In particular, what will be relevant for us is that we can characterize the radiation of massless particles. And all of this depends on our choice of path and charge of the probe particle that we are using. Okay? But of course, all of this is done in quantum field theory. So our result is going to be as good as our power of computing things in quantum field theory. And in general, in quantum field theory, we only know how to do computations at the perturbative level. Okay? And at the perturbative level, once we start going to higher orders in perturbation theory, the computations become harder and harder. Okay? So how can we gain more analytic control over the computations that we are doing in order to extract more sensible information, and in particular to enter new regimes of the field theory, such as the strong coupling or the study non-perturbative effects of the theory. Okay, so before moving, Jorge, if you want to make here the coffee break.
Sorry, yeah, this may be a very good point to stop. We have now a 10 minutes coffee break and the opportunity to ask questions. Is there any question? Alan, maybe you can comment on, well, as you said, the Wilson loop characterizes different phases. And at the same time, you're saying that you need more analytic control. Maybe you may explain why you need more analytic control, no? Why perturbation theory is not enough to determine, well, for the case of non-abelian gauge theory, the area law that you want, no?
Yeah, well, so for example, if we want to study something that's more similar to real life QCD, we know that QCD, it's asymptotically free, but in principle, we lack a description of the theory at the strong coupling regime. Okay, so here, the computation that I was showing, let me go back. Here, this is pure Young-Mills, okay? So we don't have dynamical quarks in the theory. So we are putting just probe particles, probe quarks that are moving. And in a more realistic scenario, we will need also to put dynamical quarks. And in that case, we are going to have more phenomena. And in particular here, this tau has hidden the information of the running of the coupling. So if we want to tackle these questions in more real life scenarios, we need to have some sense of control in how to enter this strong coupling regime that we know that is essential to our understanding of physics, for example, in QCD. Okay. And I don't know
that's
if
a key, yeah, maybe that's a key point, no? The equation for Yang-Mills, for the vacuum expectation value in the case Yang-Mills. In order to show this is an infrared regime where the theory becomes strongly coupled, no? Well, I stress this because maybe people are not familiar with this, and that's, I think, is a key point. You need to explore. We need to demonstrate an area law, which is this law R times T, precisely in the regime where R is large, which is an infrared regime, no? Where QCD is strongly coupled. And so you cannot use perturbation theory. You have to use something else.
Yeah, exactly. That's a good point.
And
okay, so maybe
no.
Sorry, Jorge, you were going to
No,
ask.
no, go ahead, please.
Okay, maybe I ask a question, Alan. So you are basically presenting this Wilson loop for a field. You wrote this expression for some vector A mu. So is that only for vector fields, or is this something more general?
Well, in principle, you can define this Wilson loop operator in your gauge field of reference. So if you have, for example, a scalar field, you can also define something similar as the Wilson loop. But in general, when we talk about Wilson loop, we are thinking mostly of the vector field, the A mu. But as we are going to
so
the next section, we can also consider more general things.
So this would be a spin 1 particle that this represents.
I mean, in this example that I am showing you here, for example, the U1, the A mu will be the photon field. If you want here in Yang-Mills, it will be the gluon field. So it's always the gauge field of the theory that you're considering.
Okay, but you were considering basically this, it is this integral that depends on a path, right? And then you're integrating over dx mu. So that's why, you know, in this case, it seems like to get this integral over a path, you multiply by some A mu, which is a vector field, right? And then when you were giving the example of the Aharonov-Bohm experiment, well, there also you calculate this for the A mu, which is a vector field, right? So basically that's why I'm asking, because it's not clear how you would define it for some other spin particle.
So your question is basically, how do you couple this to other fields? Oh, like it.
Yeah, I mean, for a vector field, I see this integral clearly. It is a path, okay, and then for any path, right, you can define this W, and then I'm not sure what you're going to do with this W. So my question is also, you know, what's the purpose of all these? Because you're telling us about Wilson loops and doing lots of things, but what's your purpose?
Okay, well, so the purpose, as I mentioned before, is like to try to extract sensible information from the gauge theory. Okay, this information, as I am showing you, can be many different things. Can be, for example, if I want, say that I like to study radiation in gauge theories because I feel that radiation is something important to understand. So what I am showing you here, for example, here is that if I study this operator that might seem a bit weird by definition, or I might not be familiar with this, what I am trying to show here is that if I fancy radiation and I like to study radiation, I can characterize the radiation emitted by a particle by studying a certain configuration of the Wilson loop. Okay, but say that instead of radiation, I am interested in the phases of the theory because I'm more of a QCD person, and I would like to see if the theory confines or not. Okay, so then I choose a different path, I choose a different theory, and I show you without doing any computation, of course, but I am showing you that by studying its expectation value in this specific trajectory, I can see how the theory behaves between two fundamental particles, okay? And as Jorge was saying, of course, in the case of real-life QCD, we need to understand this at the strong coupling, because if we are pulling the quarks apart, we are in the infrared and the theory is strongly coupled, okay? And as I am going to be showing afterwards, this is just like a small insight on what I can compute with the Wilson loop, but this allows me to probe many different areas of gauge theory, more, if you want, at the structural level of this. I can also try to study, for example, correlation functions of the fields, many things within gauge theory. It depends on what's the physical question that you want to ask.
Yeah, okay, it still sounds to me like this is you're doing theory in order to understand theory, but not clear what the connection to any experimental things are. But also, before you talked about these paths and you were showing this curvature, you know, and doing you're doing curved space-time. So here you seem, yes, in this plot, right? The geometry, parallel transport, yes. So here you seem to be connecting with general relativity, but also I don't understand the need, because isn't that something you can do in flat space, in Minkowski space? Why do you need to bring issues of curved space-time here, which is having to do with gravity?
As I mentioned before, I am not going to be discussing geometry. Here, right. The point of the picture of geometry is because we are used to, and in general, it's easier for us to understand the concept if we can draw it, or if we can make a picture in our head of what's happening. So, of course, the Wilson loop is the holonomy of the gauge field, and it also gives me a notion of curvature of the gauge field, but that's a bit too abstract to discuss in a general.
That I don't understand, because curvature to me means space-time curvature. So
yes, okay, but you can also define the curvature of a form, and you can go to the different levels of abstraction. But the important thing here is that we can use the Wilson loop to compare at different points the configuration of the gauge field, okay? And that is also going to be related as if the form of the gauge field has or not curvature, okay? But the picture here of this sphere is just in order to see and to understand what do we mean by parallel transport in something that we can understand. But if we go forward, and here we try to understand this analogy of parallel transport, the only important thing, if you want, is that we are trying to compare gauge fields, because since we are in space-time, and at each point in space-time, we can have different definitions of what we mean by the gauge field. So this Wilson loop allows us to compare different definitions of the gauge fields at different points in space-time, okay? Of course, it has nothing to do with general relativity, because I'm not going to be talking about relativity here. It's pure gauge theory.
Other comments?
I am answering your question, or
yeah, it's okay. It's a little bit hard, because if one is outside the field, this is all very abstract questions, and it's hard to really follow.
Yes, I mean,
so I think it is, you know,
yeah. I mean,
it's very highly abstract things that are only this one particular
I
theoretical.
Understand
right?
and understand your point, and that's why during this first half of the talk, the main takeaway message is that the Wilson loop is an operator that we can define in any theory you like. So you like the standard model, we can define a Wilson loop in the standard model. You like Maxwell electrodynamics, we can define it. You like more Yang-Mills, we can define it. You do lattice, we can define it, okay? Once we define it, we can answer different questions with this operator. The questions that are relevant to me are, if you want, the phases of the theory, okay? So this characterizes if I am in a Coulomb phase or in a Higgs phase, if I have confinement or not. And of course, this is, from the starting point, a physical relevant question. Now, the tools that I am going to use are a bit more abstract because I want to gain analytic control over the answers that I have in these questions. Okay, so I want to go beyond the regime in which we have real world applications. But the physical interesting questions are pretty clear because here I'm characterizing the potential of any gauge theory that you like, that you can came out with this gauge theory in any setup that you want, because we can use gauge theory to discuss many different phenomena. And I can also study radiation. And that's also a pretty clear physical question that I could ask, because we know that particles emit radiation. So the key question here, the physical question is, how do particles radiate when I have a strongly coupled regime? And that's a non-trivial question that we don't know how to answer in quantum field theory in principle, because we don't know how to enter to the strong coupling regime. But the important thing here is that if you want to do this in real life quantum field theory, if you want, you are going to be restricted to the perturbative regime, and you can do it and you can study it. And that's totally fine. And that will give you information, physical information about the thing that you are asking. But if you want to go beyond that and try to gain more control in order to see if there is a pattern or if there is a unified way to understand this phenomena in general, you need more tools. And that's why we are building towards finding more analytical control to answer these questions that have a physical origin. But of course, in order to gain analytic control, we start climbing up the ladder of abstraction, and it becomes harder, of course. But the motivation is this. We want to study this phenomena that's pretty standard in physical situation, and we know it's relevant for our understanding of nature.
And what is the thing that is being radiated here? Because if it's a U1, it's just photons, right? But if it's strongly coupled?
Well, that's the thing that you want to answer now. So if it's U1, it's going to be photons. If Young Mills, it's going to be gluons. In the supersymmetric cases, it's going to be a combination of gluons and scalar fields.
But if it's gluons, that you are not going to detect them. So I guess they will decay, but that's something beyond this analysis, right?
Yeah. So yeah, it's beyond what we're
But that, excuse me, Alan, I think a question by Javier is relevant because if the theory is confining, it cannot radiate gluons. No? So this is a calculation only for non-confining case, right? Or
yes, I mean, here I'm thinking about gluons because of this example, okay? But in this setup, you are not studying the radiation of gluons.
Yeah, precisely. That calculation is for Yang-Mills theory, which do not confine.
Yeah, what I am thinking here, as I am going to be showing you in the next few slides, is that if we consider the supersymmetric cases and we can study this configuration, the Wilson loop is going to be coupling to the gauge field and to a scalar field, and that gauge field, you can understand it as the generalization of what we understand. Or
what is crucial is that is conformal.
Yeah.
Supersymmetry is a crutch. Conformal is really the conceptual point, that you are in a conformal phase.
So that calculation cannot be done for non-conformal case?
Oh, the computation can be done. The interpretation that Alan was flashing, that interpretation of the log as the radiated power, that you use conformality.
Yes.
Crucially. What is the meaning of doing that computation in the non-conformal phase is different. So conformal is conceptually important to interpret the computation. Supersymmetry is a crutch to be able to do the computation.
Mm-hmm.
So what conformality is giving you is that combination is delta E. Is that right?
Yeah.
Okay.
Okay. So if you want,
other comments? Sorry.
No. Unless there are any more comments.
Well, I would like to come back to the point by Jordi. I think you explained it, but perhaps you didn't stress it enough that the thing is the following. Jordi asked, this looks like a theoretical game, but it's not really so, because one of the most important questions we have is why quarks are not observed in nature. And in words, we say, well, because QCD, because they are confined inside the proton, say. But these are words. How do you express that mathematically? How can you prove that they are confined inside the protons? And today, the only mathematical statement that one can make that is regarded as a proof of confinement is that the Wilson loop takes an expectation value and obeys the area law that Alan explained in the other transparency. We don't know any other way to show that the QCD, that quarks cannot appear as free states in nature. This is the mathematical statement that one is to prove if you want to show that a theory confines. And eventually to prove that QCD makes sense. Do you agree, Alan?
Yeah. Yeah, I mean, as far as I know, this is as you said, the only thing that we know that points toward confining. Because of, I mean, we haven't solved the problem of the mass gap in QCD, no? So.
But yeah, I'm a bit confused about this because in QCD you have flavor, so quarks have masses, and then there's no area law, right? Because you create quarks from the vacuum when you start separating them. So I guess my question is, how can I use this when I have dynamical quarks and differentiate confining theory with dynamical quark with different theories? Like, I don't know, the Higgs phase, or because there's a lot of discussion about this, right?
Yes. So as you point out, if we have dynamical quarks, we are going to be creating pairs from vacuum, and this is not going to be happening. So yeah, I'm really not sure, because I, in general, don't work in trying to prove confining or not. So I'm not really sure that I have an answer to how will you differentiate.
You can use the center symmetry.
Yes.
I think the center symmetry is not the symmetry, right? When you have dynamical quarks.
That depends on the theory.
In QCD?
No, I'm saying depends if you have matter in the fundamental or not. You have now to be specific about the content theory, the content of your theory.
Okay, maybe we should continue with the seminar since.
Okay.
Yeah, please continue.
Okay, so before the break, I was trying to ask the question of how can we gain more analytic control over the computations in order to enter this strong coupling regime and to answer more questions, okay? And what we're going to be doing is we are going to consider supersymmetry, and in particular supersymmetric Wilson loops, okay? So for us, supersymmetry is going to be just a symmetry that relates bosons and fermions in a given way. And since we are adding more symmetries to the system, we are going to be having a more constrained system. And we hope that by constraining more the system, we end up with more tools to solve them. Okay, of course, we can constrain the system too much and end up with trivial solutions, but this is not going to be the case, as I am going to show you. And let me first stress that despite the fact that we have yet failed to found supersymmetry at the experimental level, okay, we haven't seen SUSY at the experimental level. For us, supersymmetry is just going to be a tool that is going to allow us to gain more control and to enter more regimes and to find new structures and try to understand in general what's happening with the quantum field theories in the strong coupling regime. Okay, so as I mentioned before, if you give me a gauge theory, I can define the Wilson loop. And for the cases of the theories that I am going to be discussing, that's mostly superconformal and supersymmetric gauge theories. The generalization of the Wilson loop that we were discussing before is given by this expression over here, in which we see that we have the same ingredients as before. We have a gauge field, we have the trajectory of the particle, we have gamma, that's the path that's following, we have the charge hidden over here of the particle, and now we have a new ingredient that's this scalar field that also appears in the definition of the Wilson loop. But essentially, the Wilson loop is going to be depending on the same things as before. Okay, so it depends on the trajectory and also on the charge of the particle. So what have we gained by considering superconformal symmetry? Okay, and the important thing is that for certain path gamma, we are going to be able to preserve a large amount of symmetries, and this is going to constrain the expectation value of the Wilson loop. And this, in turn, is going to allow us to enter this strong coupling regime. Okay, but also, this operator is pivotal to our understanding of many different things in general in supersymmetric field theories. Okay, so let me show you a small roadmap of what can we study by studying the Wilson loops. Okay, so we have seen so far that we can study lattice theories and characterize the phases. We can also study quantum mechanics or quantum electrodynamics and study the von-Aronoff effect. And we can also study different theories, for example, Chern-Simons theories, that's a topological theory. And by studying the Wilson loop, we can understand it in terms of knot invariance. And that's an important questions in mathematics. We can also study the generalizations to supersymmetric Chern-Simons theory and study this operator. We can define this operator in a holographic setup. So we have a holographic description of the Wilson loop. And by a suitable choice of path, we can also use this holographic description in order to understand the strong coupling regime of certain scattering amplitudes of the supersymmetric theories. And it was shown that for certain path, the path integral of the theory reduces to a given matrix model in a procedure that's called supersymmetric localization. And this matrix model allows us to find exact results in the strong coupling. And this in turn allows us to make precision tests for the holographic dualities. Okay, this means that we can make non-trivial predictions for the holographic dualities. And also, if we want to study and do more precision tests, we can also study the integrability of the set of a given sector of this family of theories. So what we see is that there are many different things that we can study within supersymmetric field theories in which the Wilson loop allows us to probe them and to understand them better, okay? So now I will try to focus on supersymmetric localization and matrix model. That's the main thing that I've been working on during the last few years. So I am saying during this talk that in order to compute things in field theory, we need to do perturbation theory. Okay, and schematically, what does it mean? It means that we have a path integral that defines our theory, in which we are integrating over all the field configurations. And note here that the fields depend in general of a space-time point, and in general is a matrix valued function. Okay, because for example, if we are considering SUN gauge theories, the fields are matrix value in this SUN. Okay, and here we have the action of the theory that defines our theory. So if we want to compute an expectation value, say, of an arbitrary operator that I am calling O, and I am putting explicitly the matrix indices, we see that we have to perform this integral, okay, that in general is hard to do. Why? First of all, we have to consider all the fields of the theory. And the only way that we know how to do it is by doing perturbation theory. And that means that we are going to be considering this action as a free theory plus interaction. And we are going to be expanding around the free point. And we have to do Feynman integrals. Okay, and these integrals are harder because of the space-time dependence. And in general, if we go higher and higher to the perturbative regime, it becomes much harder to track these integrals, okay? But what it was shown was that for certain cases, in the case of supersymmetric theories, okay, by studying the Wilson loop, what people realized was that they started doing this perturbative computation, and that means computing these difficult integrals with the space-time dependence and so on. They realized that the space-time dependence was gone. Okay, so effectively, what they found was that for a given configuration of the Wilson loop, the only integrals that remained to be done were integrals over matrices. Okay, because all the space-time dependence was gone. So effectively, what they saw was that they shifted the description in terms of four-dimensional things to a zero-dimensional integral. Okay, so this at first was just a curiosity and really an interesting question of why was this happening, and it was afterwards shown that it's possible to reduce in a given sector of the theory the computation of observables to just matrix integrals. Okay, so we strip off the dependence of space-time by a procedure that's a bit technical, but it's possible to do. And the same path integral of the theory of our gauge theory of interest reduces to an integral over matrices. Okay, and these are n times n matrices. And the good thing about this is that these kind of models were studied before, and it's possible to attack them even at strong coupling. Okay, and if we do perturbation theory, since we don't have any dependence on space-time, we only have a combinatorial counting to do that you can think in terms of weak contractions. Okay, so here this model is characterized by this potential, and the potential depends on the theory that we are studying. So we start with a supersymmetric theory, we reduce the theory to this sector in which the space-time dependence is gone, and we end up with this potential depending on the theory. So for example, in the case of the most symmetric theory, n equals 4 super Young Mills, this is just a Gaussian integral, but once we start reducing the amount of symmetries, we end up with more interacting matrix models that in principle are harder to solve. Okay, so the thing that we have been doing over the past years is studying the matrix models that appear in theories with n equal to supersymmetries. Okay, and in particular, we have been focusing in the perturbative regime of these theories. And the point of focusing in the perturbative regime, instead of going to the strong coupling regime, is that by doing that, we are able to attack the whole family of theories in a unified way, instead of doing an analysis of case by case. Okay, and with this, we are able to compute the full perturbative series of the free energy of the theory. Okay, so we have the full expansion, the perturbative expansion of the free energy of this family of theories. And not only that, we were able to compute the full perturbative series of the Wilson loop in these families of theories. And what do I mean with the full perturbative series is that these expressions are closed. Okay, we have the full expression of the series, and we don't need to perform any more integrals or any more computation. All the information is purely combinatorial, and thus if we want to study this at any order in the coupling constant, we can in a really efficient way, okay? So, because we have the expression and we just see the order that we want, okay? In comparison with the difficulty that this has by using normal techniques in field theory, okay? And as I mentioned before, once we have the Wilson loop, we are able to characterize the radiation of a particle when it has this cusp trajectory, okay? And in an upcoming paper, we were also able to compute a family of 2- and 3-point functions in these theories, okay? So this might come as too much information in one slide, so let me be a bit more clear here of what I mean when the full perturbative series.
Alan, can you finish in 3 minutes?
Yeah. These are the last 2 slides. So what we mean is that now the free energy of the theory has this expansion, okay? Where here we have different graphs, that there are a specific family of graphs that they contain all the information of the perturbative series. And with this, I mean that here we have all the expansion in the coupling to the order we want, okay? And this can be computed in an algorithmically efficient way. And the same goes for the Wilson loop, in which now the graph changes a bit, but it's the same idea, okay? We can understand the perturbative expansion in terms of these graphs that contain all the combinatorial information of the computation. So to conclude, I've shown you that the Wilson loop is an interesting observable to study in any gauge theory, from which we can extract different physical information depending on what we want to study, okay? And it depends on the charge and on the path that we choose the particle to follow. And for theories with enough supersymmetries or enough symmetries in which we can enter the strong coupling regime, we are able to probe new structures that lie within the field theory. Okay, and in particular, what we have achieved is the full perturbative result for a family of theories with n = 2 supersymmetry. And in particular, we have characterized the radiation emitted by a probe particle in such theories. Okay, so with this, let me conclude and ask you if there are any more questions.
More questions, comments? Maybe I can make a comment on something that you explained very quickly. No, one may wonder why this magic of supersymmetry that suddenly a functional integral, which is something extremely complicated, becomes eventually an ordinary integral over ordinary multidimensional integral, no? An integral over matrices. And the reason, of course, is that it's a fact of quantum field theory that fermions and bosons and scalar, fermions and bosons contribute with a different signs in the loop expansion. And in theories with a high amount of supersymmetries, this cancellation between fermionic loops and bosonic loops hold to all orders. And eventually what remains is only the one loop contribution, which happened in this case of n = 2 supersymmetries. And what you actually have here is that you did compute the functional integral, but you only got a one loop determinant, which is what you will obtain by computing one loop in the theory. And that's the whole, well, and that's the reason, no? Why eventually, actually, it's not that just you remove all the space-time independence, no? There is a one loop determinant there, which somehow is, whose origin is a functional integral, no?
Yes, but yeah, I was trying to avoid a bit more of the technique.
No, I know, but just for people who are not familiar, why is that
I mean, of
things simplify
course,
so much? And the reason is that the amount of supersymmetry, which implies supersymmetry guarantees that this cancellation between fermions and bosons loops will hold to all orders. That's because, well, that's the origin. No?
I mean, it's totally necessary here, the specific configuration of the Wilson loop that preserves the right amount of supersymmetry. And in general, if we don't want to study the Wilson loop, or if we want to study other things, the supersymmetry is the thing that we need for sure.
Okay, more questions, comments? Well, if not, we thank Alan again for this very nice introduction to the topic and very nice explanations. And we will continue in the next seminar, which I think next week we have it free, but after that we have another interesting seminar. Thank you all for participating, and thank you, Alan, for the nice talk.
Thank you.